Okay, grad students, we have our third lecture today. I apologize. This is probably one of the most absolutely boring lectures in the entire world, maybe only rivaled with the one you're going to have next week. I used to do these two lectures actually at the end of the term, specifically because they were kind of more just a bunch of lists for this lecture and a lot of talking. And then the next week's one is a lot of images of basic construction. I talked it through quite a bit with some of the other profs, and everyone really agrees that one of the things that's lacking is just recognizing what basic systems look like. So in light of that, I've kind of changed the order of things. What I didn't want is all of the heavy math towards the end of the term, especially considering I can't give you assignments in the last 2 weeks. What I decided to do is switch these two lectures closer to the beginning. And now the last 2 weeks are pretty intense, but there's no assignment due. I will give you worked out problems. I will treat it like there's an assignment. I'll even post it so that you can try it if you like, but I will make the answer sheet available so that you can go through, and for those last two assignments that aren't real assignments, they aren't due, you can treat it like it was an assignment and try to practice the questions, but you know you have the PDF of the answer sheet available to you. And what I like about that is that it gives you the opportunity to practice it at your own rate. You get to see kind of what questions might appear on the exam. And also it lets you have a bit of a sense of basic construction early in the term. Going to U of T, it's a design-based program. It's definitely a less technical program than some of the other ones out there, which is so amazing because some of the most beautiful designs we see in architecture in Canada come out of U of T. The problem is that you're never exposed to anything normal. I get to be the boring old person that shows you what normal is so that then we can talk about what's not normal. So today's lecture, there is nary a picture in it. There's also no calculations. It is literally a bunch of lists. This assignment, crazy easy if you stop and look at the slides. If you don't get the perfect mark on this assignment, there is absolutely no excuse because everything is literally from the lists in this slide. So open it up on your other monitor, minimize it, go back and forth between the two. You have a week to look at a bunch of lists. So let's dig in. We're going to talk about what the elements do in a building, what their job is, how do you pick your material, why would you pick that material, when would you pick that material. So you can see that it's really not that exciting a lecture, but there's so much information in here. Often I try to disperse this out through other slides, but it gets lost in the noise then. So this way you're really focused on what I'm trying to teach you here. So the role of the structure, it's got to hold itself up. It's got a weight. You as a person, you have a weight and you're holding up your own self-weight. There's also the applied loads. You put clothes on, you put on a backpack, you drink a beer, eat a veggie burger. You've got applied loads on you. You also need to support the building envelope. Actually, that one's a better one to probably say clothes. That would be the better analogy for clothes. The thing that protects the building that most people see as structure, but isn't really. There was one of the buildings being constructed downtown that the GO train line goes right by, where the building kind of tapers away towards the inside. Most of those floors were cantilevered out, and there was a set of columns in. And I had a friend say, how can they do that? How can that floor, as they come down the floors in the building, taper away? Doesn't that building want to tip over? And I had to explain that the columns haven't changed. The core hasn't changed. They're just used to seeing all that being hidden by the building envelope. And their perception is that the building envelope is the structure itself. Sometimes we use our envelope as the structure, or it is doing some secondary work, but not very often is it the structure itself. So Sometimes it will be, but we do still need to understand the structural behavior of that. You guys are all probably taking some courses that have a lot of building envelope elements tied into it. I know there are going to be some spots where those teachers are going to come to me. What I'm going to try to do is produce short video clips kind of talking about what's happening in those conditions, just to kind of give a crossover and try to hear the structural voice talking about the building envelope elements. So the role of the structure is to support itself, support the applied loads, and support the building envelope. So what are the main types of construction? If we want to talk about what we need to pick, we need to know what is normal. Probably the most normal ones we see, there are probably 4 main normal ones. Where you live, that might change which ones are more popular. But here, we often use structural steel, reinforced concrete, stick frame wood framing, or what we would call wood construction, and then mass timber. And mass timber kind of has a lot of the same principles and theories and design kind of the scale of steel buildings. Whereas our what we call wood construction is the smaller things like houses or kind of 4-story condos. Getting into the less common now would be precast and load-bearing masonry. Load-bearing masonry, even 50 years ago, was probably in the list of the most popular construction types. It's still quite popular for maybe exterior walls, and it does have some applications. I'm not saying we don't build with it, it's just probably not in the most common elements. One of the things is that it's kind of hard to calculate. As much as we have master builders that are really good at kind of knowing what the rules of thumb are, that information has been lost. As we develop our calculations, some of the ones that are hard to calculate get lost in the mix. And then we have all kinds of really unique ones. Glass, fabric, straw bale, rammed earth. There's all kinds more of them. Kind of anything that's outside the norm of our structural elements. It could be aluminum, all kinds of different things, but they're the small minority. You might come across them in your career. There might even be people that are specialists in it, but it's not the norm. So let's talk about each material, or each of the main materials, and talk about how we would design with them or why we would design with them. Concrete, every material has its advantages and disadvantages. I am not here to tell you which one is better. I can tell you what the strengths and weaknesses of each material are, and I can tell you when we typically use each material. So concrete is adaptable. I feel like, okay, yeah, I needed to check my slides there and make sure I had the right thing in the right spot. You'll see alterations is over here. Concrete's adaptable. We can do a lot with it. We can make it work to our advantage quite readily. We can put elements where we need to. We can make things. We can really play with concrete. If you guys think of a lot of the concrete buildings in the 50s and 60s with very beautiful curved structures, we can really do incredible things with it. There's a short lead time. If you call someone up and say, I have a concrete building that I want to build, here are the drawings, they can probably be mobilizing on site in a very quick time. Depending on how busy the industry is, they could probably be there in a week or 2. You can get a very shallow depth of structure. Because concrete is everywhere in the elements, steel, we have a series of discrete elements. Concrete, we cast as kind of one monolithic element. Because every little bit of our surface is working structurally now, it means we can take advantage of it and actually can end up with a pretty shallow depth of system. And normally this is where I draw out a few things. It's a real disadvantage that I can't sketch things out for you quite quickly. But often, if in a steel building, we would have a beam that's deep, and maybe we go along where our deck is, and then we have a joist, and we go along and we have a joist. Concrete could be consistently all that deep. So steel locally might be quite shallow, but often we put a soffit or a ceiling under there that gives it the illusion of being much deeper. Finishes. Concrete can often be the finished surface. If you don't have any kind of other requirements, you can often use concrete for the finish, and you can make very beautiful concrete finishes. If you have a good contractor, basic requirements for concrete can end up with a gorgeous finished surface. But you can move on to even more kind of explicit things with board formed concrete or other surface formed concrete. You can cast in elements, you can sandblast it, you can do all kinds of things that kind of really gives concrete a gorgeous finish. It's non-combustible, which means it doesn't burn. It also has a good fire rating, which is not the same thing as being combustible. It performs very well if there are other things in the building that are burning. It itself won't burn because it's non-combustible, but the things in the building can still burn. And if those things are burning, the concrete still performs very, very well, assuming it has the proper cover, which is the thing we'll talk about when we talk about concrete more in depth, when we talk about kind of the math behind concrete. This is more just an overall heading to introduce you to the materials and construction types. Acoustics. Concrete can have very good acoustics. It's ductile, which most people think concrete isn't ductile because the material concrete itself is quite brittle. But when we're talking about concrete in engineering, we are not talking about concrete all by itself. We are talking about reinforced concrete. That means there is steel embedded in it. Now, ductility is when you put a load on something and it moves, and you can have large movements without it failing. And that's the definition of ductility. We like ductile things because it absorbs energy or dissipates energy, if you want to think of it that way. So in high seismic zones, we want our building to move so that we don't have to resist as heavy forces, because those forces are going into moving the building, not breaking the building. So we like ductility, and if we put steel inside our concrete, we can get a very ductile building. Concrete is inherently corrosion resistant. Anyone who's driven under the Gardner might be like, you're crazy. Do you see that concrete spalling off the underside with the exposed rebar and all of the repairs that are happening to it? Well, the Gardner is a building that is well past its life expectancy. It was designed to have a 30 to 50 year life expectancy, and we are well past that. I can see my son my 2-year-old through the window, staring at me, just staring at me. Duncan. So it has outperformed its expectations. Back in the day, as much as it does have good corrosion resistance, the Gardner's probably, not only did it exceed its life expectancy, it is probably in one of the harshest environments. We literally salt the surface of it all the time. The water runs off down the side, and concrete is not impermeable. Water does get into concrete. It will wick concrete into it. On a rainy day after the sun comes out, you've probably seen that concrete takes a little while to dry. That's because it's got a lot of that water kind of absorbed into it. So that water, that salty water, can now come down into the concrete, and steel can rust very easily. Now, steel, when it rusts, it expands to 10 times its size. So when you see a big chunk of rust, the amount of material that really was only 1/10 of its original size. So if you have a big spall of steel that's big, it was just a micro fraction of steel. But when it's embedded in concrete, as that steel rust tries to expand, it kind of pushes outward, and that concrete can start to spall off. So it's still got great corrosion resistance, but it's good to understand where the failings are of it. Concrete has some real disadvantages. It doesn't have long spans. We're limited by a few things. We're limited by, our formwork and our supports. We're limited by the fact that it is very heavy. You can see that one right down here. We are limited by how we can reinforce it. So, concrete has some flaws in that it works really well, but often we kind of limit it to some smaller spans. So if you want those really large span buildings, it doesn't mean you can't do concrete. It might mean you have to understand the cost and the expense of that, because it's not inherently kind of geared to that. Or maybe you need a hybrid system where you introduce other elements. It's not great for alterations. A concrete building, even though we might only need a small amount of it to be structural, once it's cast, it's all there and you don't know what part is structural and what part isn't. So in a steel building, we have steel columns locally. Maybe sometimes we have a brace, but we have our structure locally. And even in a floor, we have beams and joists, but there's often spots that have no structure. Concrete, everything is the structure. The thing that makes it really great for being a shallow depth of structure is the reason it's not so great for alterations. If you want to come in later and say, I want to put a door in that wall, you need somebody to analyze that. I have a project that I did a couple years ago. It was at High Park, and they wanted to put a door opening in a concrete building. Now, this one was pretty easy. You could look at the building, and every 6 meters, they had a very long shear wall. Without even doing the analysis of the building, it was very easy to see that one small door opening in one section of one wall was totally okay. The building department, the building department's great, but this one person on that particular day was not happy about it and demanded a 3D dynamic model to prove it. Now, that's something we do when we design a new building, where we're designing all the elements, and is weeks of work. These people wanted to put a door in, and it worked by inspection. I wrote a memo, explained that it worked by inspection, and they said they wouldn't accept it. Now, you have to remember, this person who owns the building just wants to put a doorway in. Now, all of a sudden, they had to pay an engineer for weeks worth of work just to say they could put in a door, more than the cost of putting in the door itself. Rightly so, I explained this to them and said that I was willing to kind of take a stand on this. I went through and kind of did some quick back of the envelope calculations and just showed that taking the door out was taking out 1% of the lateral system on that floor. I wrote that memo. The building department still didn't want to accept it. So I wrote yet another memo that pointed out that if we had assumed the walls were, we often, when we're working between metric and imperial, we might say that the wall is 203 millimeters thick, meaning 8 inches, or 200 millimeters, which when we switch to imperial, we often just kind of round off that 3 millimeters. That door opening was less of a change than the kind of difference in two engineers doing the calculations using 200 millimeters and 203 millimeters. So when I wrote that memo, the building department was okay to say, all right, put your door in and leave us alone. I don't often like to kind of it's not my mission to kind of go up against authority. That wasn't what I was looking to do. I just didn't think that it was a fair burden for the owner to take that on when it so reasonably did not need to be designed to that level. So always something to bear in mind. That isn't the place to start. Don't go to the building department like guns blazing going, no way, buddy. But sometimes it might be the appropriate thing to do. But that's what makes concrete hard to deal with alterations. I'm sure they've had a lot of people just blow holes in concrete walls, not thinking of structure. And so they just have a firm policy of why you can't do that without an in-depth analysis. So I kind of get where they were coming from. It's because alterations are hard in concrete buildings. It's sensitive to weather. Once we're building it, it's really dependent on weather. Concrete is, as much as our steel is kind of made in a kind of industrial plant, there's chemists on site testing it. It's kind of a really scientific, thoughtful process. Concrete, we say this is how strong we want it to be, And a bunch of people throw a bunch of stuff in a truck, it gets mixed up on its way to site, and they pour it out. We literally do not know if it's strong enough until after it's been cast, because they take little samples of it and test it at 7 days and 28 days to prove that it is in fact strong enough. So you have to be pretty good at making the mix, but water is a part of the mix, and not a lot of water. People think there's a lot of water in it, but it's not a high percentage of water in there. That means a really humid day can make a difference. Really dry days can make a difference. It can't cure, probably, don't say dry. Concrete cures. It doesn't cure well when it's really cold. So in cold weather, concrete construction pretty much grinds to a halt. There was kind of a super warm winter in 2012, 2011, and the construction industry basically was able to work all winter long. The next year we had record cold weather multiple times, and at the time I was working in an office that was right beside a concrete building being construction. They basically stopped work for a month and a half. Contractors have to build that risk into their price. And even then, sometimes they might be screwed over because they can't predict the weather. And it's not fair for them to bear that risk on their own. The owner has to bear some of that risk as well. But they are the experts. They do kind of understand better what the implications of that are. So there is a bit more onus on the contractor, but they can't be responsible to bear that all by themselves. The weather is the weather. Quality control. The labor force for concrete, there can be really skilled workers within it, but there can also be people that just go out and lay the rebar out without really understanding kind of the thought process behind it. And there's lots of rebar, lots of little tiny pieces of steel in one big area, and that steel is critical, and that might not always be apparent to the workforce. A steel beam, it's pretty obvious that that thing is working. I have a project that I was actually just working on a week ago, and my drawings were pretty explicit, and the contractor's just like, I don't know what you're talking about. Why do I need that steel there? Because it's doing the work. And they're like, I don't think so. Let's agree to disagree. Which was, no, it needs to be there. It's doing its work. We kind of talked through why it's important and why it needs to be where it is, and also how they could go about laying it out. This project was maybe a bit outside of their skill set, so we had to have a few conversations to kind of talk through how to put that in. But that's a risk you run when you're dealing with concrete. That's why quality control reviews is really important. You need somebody to come out and take a look that does understand the implications to make sure that everything is where it needs to be. In fact, a lot of concrete buildings will actually have a third-party review. Actually, most construction does, but for reinforcing, there'll actually be another person on either the contractor's behalf or sometimes also even on the owner's behalf that will come and write a report to see if the steel matches the contract drawings that's embedded in the concrete. Weight. Concrete's heavy, which sounds crazy because steel is heavier than concrete. But because we need so much concrete, because it's at every little incremental part of the structure, it adds up fast. And it's not as strong as steel, so we need more of it, which means that weight starts to really add up. I showed you guys an image of the NCFS headquarters at 30 College, where they were putting all kinds of stuff on the rooftop, and we looked at what it would take to just add concrete and embed rebar in it to make that system work. But we got into the cyclical effect that the more concrete we added, the steel that was in it already wasn't strong enough to carry its weight. So it's not often that we have to say, no, you can't do that. But that was a situation where it was literally, no, we can't just add concrete with rebar in the top to make this system work because it's just simply too heavy. So we had to come up with kind of a new, unique way to reinforce that concrete. There's a fly in here, sorry. There's another thing that's not on this list, and I'm always writing myself notes of things to write on here. And this one's really important, I think. So hopefully by the time you read this, you'll be seeing an added thing to this. you have to build a concrete building twice. The concrete's just kind of this liquidy, gooey blob until it's cured. You need something to hold it in place. That means you have to build your formwork that holds it in place until it cures. Sometimes we try to incorporate that formwork into our structure, like a concrete on metal deck system, for example. And then sometimes what we'll do is form it, let the concrete cure, and then take the formwork and build the next floor. One of the real kind of cost efficiencies in a concrete building is when we can reuse that formwork. That's what makes it cost efficient. So let's take a look now at some concrete applications. Concrete works really well in that mid-rise level of construction because often those mid-rise buildings tend to be somewhat repetitive. So we're talking about office buildings and apartment buildings, and this is where I had stressed that formwork is a big component of the cost of concrete buildings. So if we can reuse our formwork, we can drive the cost of that system down. It makes it more economical. So literally it's the same floor print again and again and again, and we take the formwork out, bring it up to the next floor, and cast that floor. So that works well for mid-rise apartment buildings and mid-rise office buildings. It works really well for parking garages. Again, because the structure is at every tiny little spot within our surface, we don't have to worry about we've got heavy loads localized that move around. In a steel building, we'd have to do something in between our joists or our beams where we've got deck, because the deck itself might not be that strong. So once we're making that thick enough to carry the individual tire load, we've often got something thick enough that can carry the entire system. So it lends itself really well to parking garages. Again, parking garages are usually 3 to 4 stories and repetitive. So it works well with that whole formwork application as well. Foundations are kind of just a no-brainer when it comes to concrete. There are definitely foundations that aren't concrete, but those are the rarity, not the norm. Because our soil is everywhere pushing in, our concrete works really well to resist that load everywhere. Also, we don't have to bring a built thing to the site. We make concrete on site. And when we're in a big pit and a big hole where we don't really have access, we're going down weird things, concrete works really well for that because we bring in a bucket of wet goo at a time. If you guys have ever seen those big kind of long, kind of weird kooky things that pump concrete from the truck to where it needs to be, that's what I'm talking about. You can actually kind of just pump the concrete quite far and not have to worry about bringing a whole truck or a whole thing down into the hole. So like I said, some of the cost factors. Formwork is a huge cost factor. If we can reuse that formwork, we can drop that cost down. Strength of concrete. In the normal range of things, the strength of concrete isn't that big of a deal. There's a nominal cost kind of difference between 25 and 35 MPa. We're going to talk about what that means later on. Don't worry about it. We'll spend a whole lecture in Structures 2 talking about that. But when we get into the kind of the really high-end concrete, cost can be a big factor. So if we're doing, a 60-story building, some of that concrete needs to be really high strength, or maybe we need special additives added to it to make it cure faster, or kind of deal with some of the spalling issues or finish issues. That can add real cost. So I might even change that in slide 5. I might add to cost concrete mix or additives. Spans. Like I said, concrete doesn't do well doing long spans. If you want to do long spans in concrete, the cost goes up very quickly. It's not a linear cost addition. If you want to increase the spans of your concrete, it goes up quite a bit faster than the weight and the amount of concrete you're using. And like I said, time of year is a huge cost factor in concrete construction. Too hot a summer, hard to do concrete. Too cold a winter, hard to do concrete. So really kind of understanding your kind of peak concrete season has to line up with your construction and the mobility, when you have contractors, when you get your permit, all of those things can add into the time of year of construction and can have a big impact on a concrete building. So those are kind of the quick thought processes of concrete and our concrete construction material. Let's talk about steel construction. Again, I'm not here to say what one's better, but concrete and steel are probably two of the most popular ones that we tend to design with as architects and engineers. There is a lot of wood construction, both residential and mass timber, and I'm going to touch on those. The mass timber is kind of coming up in the world, and residential is probably the most popular building material, but it's less kind of involved with the architects and engineers. Often homeowners can do it themselves, or contractors can do it themselves. They can follow Part 9. So as much as there's a whole industry in engineering and architecture with wood as the material source, it's not as prevalent. So what are some of the advantages of steel construction? What are some of the advantages of steel construction? Well, it's strong and stiff and light. So that makes it kind of an easy material to work with. Now again, I said steel is way heavier than concrete. Just to kind of give you a sense, steel is about 77 kilonewtons per meter cubed. So a 1 meter by 1 meter by 1 meter cube of concrete is 77 kilonewtons. Concrete is 23.5 kilonewtons. So it's actually about a third of the weight. But steel is so much stronger than concrete. Concrete's about 25 MPa and steel is 350 MPa. So it is so much stronger that we need so much less of it that for the building system, it ends up being a much lighter material. So if we had as much steel as we had concrete, it would not be lighter. It would be much, much heavier. But we don't need as much steel. In fact, we need so much less steel that it actually ends up making the system much lighter. We can do really long spans. If we don't have members long enough, we can make our own members. We can make trusses where we build it up out of smaller members. So we can do ridiculously long spans with steel. We have small columns. Because it's so strong, we can have a much smaller column. If you have rentable space as your primary driver, if your client is kind of creating office space or retail space, every little square foot is marketable, which means if you have a smaller column, you can actually have more retail space on your floor and drive your rents up. Quality control, really easy in steel. First off, the material of steel itself is made, like I said, in kind of this industrial plant where they actually have chemists and experts and specialists kind of monitoring the creation of it. How they roll it out and make the shapes is very, very precise. It doesn't look like it. It looks a little chaotic, but it is a series of machines essentially rolling it out to be the exact size and shape that we need it to be. And then you have a team of specialists who are usually erecting it and installing it on site. There is a second set of engineering eyes that looks at steel in the shop drawing phase. So the engineer creates their drawings, the base building drawings with the steel on it. But then the fabricator, at least here in Ontario, this is different in BC and California, the contractor engineer, the fabricator's engineer, will design the connections. But that means there's two sets of engineering eyes looking at everything. And then the base building engineer looks at the shop drawings, and then it's really easy to see if something doesn't match the structural drawings on site. It's a lot easier than picking out those pieces of rebar that aren't in the right spot. You can look at a steel beam and say, no, that doesn't seem deep enough. That looks like it's the wrong beam, or you don't have enough bolts or bolt holes in that right there. So steel has really good quality control. it goes up fast. Once the steel makes it to site, and you'll see over here in disadvantages, there's a long lead time. But once it makes it to site, it goes really, really fast. Some contracts, or at least the way the funding works from the bank, nobody gets paid until things are mobilized on site. And in those situations, concrete might be an advantage because construction kind of gets going right away and everyone can get paid their first round of payments. Steel has the appearance that nothing is happening for a really long time because nothing's going on site. But concrete, every time you pour a floor, you have to wait a week until you can do the next floor. So it can be really slow to kind of just get that system going up in the air. Whereas steel, you could build several floors in a day if you had a good crew and enough crane power to do it. So as much as it seems like it's slow off the get-go, it can end up being the same or faster, depending on really the project. But it could end up being easily the same amount of time as the concrete building. Future alterations, really easy in steel buildings, mostly because they're probably not even structured there. If you can look at the structural drawings, you'll know that the columns are here, and you want to put your doorway here, unless there's a brace there, no problem. Even if you do need to move an element, you can see quite easily in the drawings will often say kind of what the load is on it and what we would need to do to revise the structure to make that happen. So even if there's cost and work involved, it's really easy to understand the implications of that alteration. Fabrication benefit. It's really easy to make things out of steel kind of in the shop, kind of off-site to create exactly what we need. It is non-combustible. That means it will not burn. If we come over to disadvantages, you see it has a poor fire rating. Like I said with concrete, fire rating and combustibility, not the same thing. Concrete is both non-combustible and has a good fire rating. Steel is non-combustible but doesn't have a great fire rating. When concrete is exposed to high heat, it loses strength. That was one of the really tragic, unfortunate things in the 9/11 Twin Tower collapses. As much as it was designed to withstand an explosion, actually even a plane hitting it, the unexpected consequence of it was that jet fuel burns at such a high heat, and it actually weakened the steel to such a degree that it inevitably collapsed. There's a lot of other things going on in there, most of them kind of unanticipatable, but they did actually design the Twin Towers to withstand a plane hitting it, and it did withstand the actual impact of the plane. The building withstood that. 2 planes, and so it was kind of inevitably the fire was a big part of that. Like I said, there was a lot of other things, and that's not what we're gonna talk about today. But I was in my kind of last year of in-depth structural analysis classes when that happened, and so we spent a lot of time analyzing that and talking about that at the time. Long lead time. It has a long lead time for the exact reasons I said. We have a lot of good quality control issues with it. It goes off to someone who reviews the drawings, creates their own drawings, designs new elements or checks all of the connections, kind of does their own kind of due diligence checks. And then those drawings come back to the base building engineer, sees if they match their drawings, it goes back off. They create everything in the shop. So it's not happening live on site. They're creating it off in the shop. The real advantage there is they're inside a building. If it's a blizzard outside, it doesn't matter. Work can still be happening inside the shop. So it's not susceptible to weather the same way, but it gives this appearance that nothing's happening on site. And then eventually it'll all come to site. So we've got a long lead time on that there. So where would we build with steel? When are the kind of common times we build with steel? This isn't to say the only time. We can do concrete, steel, wood in pretty much any application. I'm talking about what's normal. You will always be able to find precedent that are not in these applications lists. Of course you will. Architects and engineers are always pushing boundaries, but we're talking about the norm or the kind of most common precedent type buildings of these materials. So very low and very high buildings. It's really easy to kind of move steel up and kind of get it up high. It works well for going up on low buildings where concrete might not, because formwork is too much of a cost inhibitor for it. Shopping centers lend themselves really well to steel buildings. Hospitals, schools, they're not always built out of steel. You're going to see there are other materials that have these same elements on their list, but I'm just saying that they lend themselves well to steel as well. Warehouses and industrial buildings, probably 99% of them are made out of steel. Because of those long spans, they just lend themselves so well to kind of plants and construction and elements happening inside a building shell. Steel plants are obviously made out of steel, but even a lot of concrete plants are probably made out of steel because they have where they park all of their big trucks, probably all steel buildings, just because it lends itself so well to kind of that big wide open floor plate that we would need. Systems buildings. So this is, you might have heard of something called Balin buildings or Butler buildings. They have different names depending on who the local kind of rock star is in that application. But those are buildings where the architect relinquishes a lot of control on what the building might finally look like. And they accept that it might not be as pretty or refined looking as they want, but man, can they kind of pare down that engineering to the bare bones that they need to make that building stand up. So very utilitarian. If you've ever been in a hockey arena, you've probably, if you go to hockey arenas a lot, you have probably been in a systems building or a Balin or Butler building. They do a lot of that style of construction. And next week, we're going to look at a lot of pictures of these different types of construction. And I'll show you some pictures of the steel ones. I think next year, I'd maybe break these lectures up a little bit. I'd do concrete and then the concrete images, steel, and then steel images, and just spread it out over 2 weeks, just so it's not so dry. But you guys get it this way. Okay, wood. I'm trying to talk about both types of materials here. I don't think I break it up. I keep saying I'm going to do that, but when I started this, mass timber, it was hard to even be allowed to do mass timber a lot in Canada. But the rules are rapidly changing about when and how and we're allowed to build with wood. So we're seeing this real emergence in there's another thing I'm going to add to the concrete disadvantages. I'm going to add environmental. If anyone has ever heard about kind of the sand cartels, just going back to the disadvantages of concrete, sand is like a hot commodity in the industrial world. There's all kinds of facts that my husband has scrolled away in his head about kind of the detriment of the sand industry. But it's a huge part of the concrete construction. That's not to say that concrete is like inherently horrible, but there are some real disadvantages environmentally with concrete construction. You'll hear a lot of concrete contractors say otherwise, but I think the statistics are there that it is just bad for the environment. All construction is, let's face it, bad for the environment, and what we're trying to find is the ones that are the most neutral, which also means that in wood, I'm going to add that it is probably the most environmentally neutral material we have. You can actually have it be truly environmentally neutral if you're in the right country with the right guidelines and the right laws and the right methods of construction. because it can encapsulate so much carbon. But that's a bit beyond what we want to talk about here. I just feel like I should add that to these slides because it's something that's becoming much more prevalent the more we're constructing with wood in the industry. Wood, I'm mixing up here a little bit residential and mass timber. Maybe this is even the time to break that up. I might add a separate slide just to kind of point that out, and then going forward in future years, really kind of distinguish between those two. Economy, if you're talking about residential or stick frame construction, and here I'm talking about you can walk over to Home Depot and purchase the wood, we're talking about residential construction or nominal wood construction. It is economical. It is cheap. You can walk in, you can buy the lumber you need. There is a very short lead time. Like I said, you want to build a deck, go to Home Depot today, come back with your materials, start building your deck. Right now is a bit hard because there is a shortage on decking material in the industry. And in fact, we built a deck a couple weeks ago, just a tent platform at our cottage, because our cottage is like this tiny little place, and we built a tent platform, and the wood was essentially wet. And we're going to see why that's important in structures too, when we talk about the kind of constructability and the science behind wood construction. It goes up fast. Like I said, we built a tent platform a week ago. We built a 20 by 20 deck platform in a day. So it is quick to build with wood. You just need some tools and you can go ahead and build it. That also means there's an available workforce. You want to build a deck? Call a couple of your pals, have the girls come over and start building that deck. You can knock it off really quickly. Wood has shockingly good thermal properties. My cottage on Lake Nipissing is a unique kind of construction that wouldn't stand up against any kind of rigorous mathematical calculations, but that's the way I bought it, and it's been standing since the 50s, so I'm not gonna pick at that thread too much. But it is a series of milled 2x6s, and so full size 2x6s, so not 1.5 inches, but actually 2 inches thick, just a series of them going around the building. And what you see on the outside is what you see on the inside. So there is no finishes, there is nothing. The outside has a coat of paint on it. That is all that is on it. I have gone up there in the winter when it's been -15, and lighting the wood stove has gotten that place comfortable enough to go around without a jacket on in your normal clothes. If it's windy, it was not okay, because wood has like knots of holes and cracks, and that all would come through. But without any wind, when it was just cold outside and warm inside, that wood was enough insulation. I think a 2x6, or like a nominal 2x6, 1.5 inches is what, R2? About R2? R1? R2?
Something like that, yeah.
Somewhere around R2, which is not nothing. A regular piece of glass is probably R.25, yeah, essentially 0. So you have a big building with all kinds of windows. That is a much bigger way to have a kind of a thermal problem in your building, which is why we have double and triple pane glass. I'm not the expert on that. Obviously, you guys are probably doing a lot of that in your other classes. But a single pane piece of glass is going to be much more willing to kind of lose heat through than the wood element in your building. Treatment options. Wood has a lot of problems. It decays. You can see that over here. It has natural flaws. There's all kinds of things with it. But there are treatment options. We can do a lot of things with wood to kind of help deal with that. It also takes other treatments really well. We want to oil it, we want to stain it, we want to paint it. There are all kinds of things that you can very easily do with wood to kind of make its appearance look the way you want. So there are practical treatments we can do, and enhancement treatments we can do for visual. It is corrosion resistant. Which seems kind of crazy because I said it's got decay over here, but we're talking about, chemical corrosion here. It is fire resistant in large dimension elements. So there are kind of two reasons why that's the case. The first one is that if the element is big enough and it burns, it builds up a layer of char. How many of you have built a campfire? I can't see you raise your hands. I'm assuming you're all doing it. But if you've ever built a campfire, you don't just take your log and sit it in the fire and walk away. Actually, let me come back to that. If you put a big piece of wood in the fire and it burns, it will often tend to peter out eventually. If you can get that thing burning, it will peter out, and you'll see that it's got a layer of charcoal around it, and it's got the good solid wood still inside it. So our large dimension pieces of wood may burn because it is, as you can imagine, combustible. But once it's burnt off a layer around it, we're left with a good chunk of workable material inside it. It's not as strong as the original amount, definitely not, but in a fire, you're not going to be experiencing your full loads. So we're talking after a prolonged burn. So let's say our building has been burning for an hour and our building has a layer of char around it and we've still got good solid wood in the center. And at a 1 hour of a burn, you're not worried about a full assembly load in your building. You're not worried about 4.8 kPa of people jammed on that floor. You're down to 1 kPa or 0.5 kPa, a very light load for those last people that need to get out or the fire department coming in to help extinguish that fire. There's enough material left to resist that load. The second thing, so the reason that doesn't work on small scale elements is that as it burns away, you only have a small element, you've burnt all the way down into the middle of that element. So a 2x4, if it's going to char an inch around the outside and it's only 1.5 by 3.5, you're left with no structural material left after that 1 hour burn. Is it about an inch an hour? What is it? Something around that.
Inch and a half, 41 millimeters.
41 millimeters, so an inch and a half an hour. As we burn that down, regular construction, there is nothing left. But in mass timber, when we have big elements, or even if you're doing construction with some of the larger elements, maybe a 6x6, you can have structural properties left after a burn. The other thing is about kind of how the fire can propagate. In residential construction, you've got a piece of plywood, usually, and a series of studs. You light a fire gets in that little hole there, and everything is going to burn. So this is where I said, if you take that log and just sit it on the fire, it's hard to actually get it to burn. What you do is you cut it up and you stack it up and you put your fire inside it, and what you have is a series of radiating or re-radiating surfaces. The heat bounces off each of the surfaces and helps contain that heat and and able to propagate the fire there. In mass timber, you have a big element here, or maybe you have just a big flat plate of wood where it's hard to get that originally ignited. So there's kind of two advantages there in the fire resistance of large wood elements. The disadvantages, obviously, it's combustible. Both our steel and our concrete were not combustible. There are many types of buildings that just flat out have a rule that you cannot have combustible material. Often they're working hard to compartmentalize it and say, this zone of this type of buildings can't be, or you need this part to be non-combustible. But that can be a real non-starter in wood construction. If it is non-combustible, you can't really do anything about that. Well, that's not true. You can often encapsulate things. There are some workarounds for those things. It's got a bit of a disadvantage in vibration. The really big disadvantage in wood is its connections. So wood is kind of this two pieces of organic material. Connecting them together is really hard. Anytime you try to drill a hole in wood, it's prone to splitting and cracking. We can't put our connectors too close together. We need chunks of material in between those. So if if any of you have seen kind of the ubiquitous BC mass timber construction, you've probably seen big Douglas fir glulam elements with big painted black steel connector plates. That's because the connections tend to govern what these things look like. Member sizes. If you're talking about, with mass timber, trading out a steel building for a mass timber building, they can work in a very similar way, but the mass timber elements are going to be much bigger. There might be a very good reason why you would accept that. And aesthetics, environmental, there are lots of good reasons to say, I want to go ahead with that. But it's important to understand that it's not a straight trade-off. Your floor plate is going to get bigger, your columns are going to get bigger. There's a lot of kind of implications on that. So what things work really well in wood construction? Well, obviously small residential buildings, a lot of farm buildings, kind of not that industrial scale of farm buildings, but barns, sheds, those lend themselves really well to residential or a nominal wood construction. Temporary structures, again, because they're quick to mobilize the force, the materials are readily available, you can often go build temporary structures. In fact, that is the exact premise of our concrete construction. We build a temporary structure out of plywood often and some supports to build our concrete building ultimately. And special structures. So this probably needs to be expanded a little bit going forward, because that used to be those rare buildings that would be in mass timber. But in the past even 3 years, the amount of mass timber construction is skyrocketing. When I started teaching this course 6 years ago, I had worked on a handful of mass timber buildings, none of them tall. The code changed a couple years ago to allow buildings over 4 stories in wood. There's also amendments coming to that are going to allow even higher. I know my husband's company right now has, how many high rises in wood do you think you guys are working on right now?
8 maybe?
8. That's one structural engineering firm in Toronto, and I know probably most of the others are in the same boat. So that's a lot of wood high-rise construction happening in the next 5 to 10 years in Canada and the world. So precast, we're not going to spend a ton of time talking about precast. It's not kind of one of the predominant construction methods. It's durable. There's lots of quality control because they literally, like steel, make it inside a building and bring it to site. The really big thing about precast is we can pre-stress it. So concrete is really great in compression, absolute crap in tension. In fact, we say it has 0 capacity in tension, but in compression, it is fantastic. So what we do when we pre-stress is we'll put a plate here, we'll put a tendon through it, we have concrete here, and then we pull really hard against another plate here. So we squash the concrete together so that if we tried to pull on that concrete, what we're actually doing is unloading that tendon before we switch to putting the concrete in tension. So we can kind of build capacity into that system. It's a lot of hard work. There are very controlled systems. You can imagine you need it in strands inside the concrete. It's something that's growing in popularity too. It used to be done a lot in the 50s and 60s. And then it kind of fell out of favor. You didn't see many of them in the 80s, 90s, and early 2000s. But from 2010 to 2020, I can think of 5 or 6 projects at Blackwell alone where we see pre-stressing kind of coming up in the systems. Core slab or hollow core systems, which we're going to talk about again going forward, they actually made really smart use of pre-stressing kind of in their development of their systems. They actually have strands of steel instead of rebar tensioned inside those slabs. long spans. So as much as we can't do our our cast in place concrete long spans, we can actually do pretty good with long spans with our precast concrete because we're controlling it, because we have the option of pre-stressing it. And you can pre-stress cast in place too. I'm not saying you can't, but it's a lot harder. We can end up with long spans. If you've been on a highway, under a highway overpass, you've probably seen precast concrete girders that are doing a long span type of work. Finishes. This is one of the really nice things about precast concrete. They cast that concrete against something pristine, often a steel plate of some sort. Our concrete in the field, our cast in place concrete, is usually cast against a piece of plywood. Sometimes that plywood is on its 7th reuse. So there's bits and chunks stuck to it. When you take it off, all of that is going to read in your concrete. If we have this pristine, smooth surface that we're casting our concrete on, you are going to get the most gorgeous surface finish you can imagine. So often precast might be used to be the actual edge that you see as your beautiful finish. It, like concrete, is non-combustible, has good fire ratings, and can have good acoustics. Disadvantages: it's non-ductile. Sometimes that's because of how it's connected. It's not reinforced in quite the same way where we have all of the rebar in it. Even our pre-stressing might not meet the ductility requirements. We often have kind of small, refined elements that are highly precise doing the work where we don't have the same embedded steel in it. It really only works on regular grids. The cost effectiveness of it means you're buying 100 of the same thing, which means you're building a relatively regular building. That's what makes it cost effective. And same as concrete, future flexibility is really hard. So you'll often see precast for parking garages. It works well for motels where there's a lot of repetition. Apartment buildings, schools, precast a lot in cladding, where they can produce panels that they can then hang as the facade or and attach their building envelope to around the building. Stadiums. A lot of the elements within stadiums are precast. So whether it's our bleachers or elements around the floor, there's often that ring around it. Those lend themselves really well to precast. Often too because we've got a nice smooth finish on those. Structural masonry. This is one that was probably the predominant construction method in the 40s, I would say, and it's kind of fallen out of favor now. Again, I said some of that has to do with the fact that our building codes require kind of in-depth calculations, and masonry, as much as we know it works most of the time, it's harder to do that calculation and that analysis of it, and it has some inherent flaws within it. It's durable. It's economical. It's really kind of cheap to kind of knock up a masonry building in a couple days. It's non-combustible, good fire ratings, the same thing we have with our concrete and our precast. It's decay and corrosion resistant. So many of those advantages we've already seen in precast and concrete, where really masonry is tiny precast elements that we're stacking together with bits of gooey concrete. We're basically using bits of concrete as glue to hold together all our precast elements. Speed. As much as I said we could knock it up in a few days, we're talking about a 1 or 2 story building. It is actually relatively slow because we take each block and hand place it, do a bunch of stuff to it, come, place a new one, do a bunch of stuff to it. So it really slows the process down. It used to be almost anyone knew how to build masonry. It was so popular. Now there are very few kind of high quality masons available in the workforce now. As the popularity of the material's fallen out, the jobs in it haven't been there to sustain the kind of expertise in it. So some of those things that we used to be able to do are no longer there. This is probably a good place to mention kind of labor cost versus material cost. In the 40s, 50s, and 60s, material cost governed our systems. Labor costs were relatively cheap. So we did whatever we could to take material out of the system by throwing labor at the problem. We solved all of our problems with labor, not with material. So concrete buildings in the 50s and 60s, beautiful sculptural projects, mostly because taking the material out that we didn't need ended up with those beautiful curved surfaces. They were actually highly functional and economical at that time. Today's market, we are in a very different market. Labor is expensive and material is really, really cheap. So today we do everything we can to take labor out of the problem. So if that means we're using the same basic squared off formwork again and again and again to cut down on the labor of installing that, curving it, making it beautiful, and it doesn't matter that there's extra material that we might not need in the analysis in there, because that is the more economical solution. I've been talking a lot, Dave and I have been talking, my husband and I have been talking a lot about, we're on the cusp of a new kind of economic system in construction. We're seeing more and more, even in the past few years with these slides about mass timber, where what seems to be governing our system is less actually even about cost. It's about the environmental aspects. It's about the sustainability aspects. It's about the future iterations of your project. The most expensive thing in the world is to knock down an old building and build a new one. That is a whole building cost lost, an environmental loss. The cheapest thing to do is kind of reimagine the building you already have. And if we planned our buildings to plan for changes in the future, plan for future flexibility, we save the cost of tearing that building down. So we're kind of on this cusp of, we don't even know what I imagine people in the 50s and 60s thought that was the way construction was going to go for a long time. And here now we have a completely different cost-based system in our construction process. In 10 years, we're going to see, and COVID adds a whole new implication to that. We're going to see that we cannot predict exactly. The people who do predict it, there's going to be people predicting 15 different things, and the people that do predict that will be seen as heroes. But they just got lucky that their prediction happened to be the one that ended up being right, because we don't know. We don't know what thing is going to govern our cost systems going forward. There will always be a component of labor and material built into that, for sure. But there are so many more things that we're starting to see that we have to incorporate into that. Sorry, that was a total side rant that I just really felt important to share with you guys. Disadvantages, there's limited loading conditions. There's not, it's really good kind of in bearing. It doesn't do good for in too much bending. We don't do beams out of it at all. They used to do beams out of it. I actually went into a building under renovation one time where we thought we knew what the construction material was. We took off kind of the finishes and saw that it was actually masonry beams made with rebar threaded through it. That was a difficulty because we wouldn't even allow that now. That it really kind of put some limits on what we could do in that renovation in the end. But if you go around an old building in Toronto, you might find that construction type. Proportions compared to the other materials. First off, it's only available in the sizes it's available. Usually 90 wide for a brick, 140 if you're getting into your bigger masonry. 190 is pretty common, 240 and even 290 as our widths of things. So we don't have a lot of play in how we make it. Also, we end up with things that are bigger than what we might if we were building the concrete version of it or the steel version of it. Masonry works really well for walls and low-rise buildings. Foundations, not retaining earth. Now, when I moved to Toronto from Nova Scotia, I was designing a house, and my boss came to me and said, and so they're doing masonry foundations. And I laughed and I laughed and I was like, what are you talking about? Because in Nova Scotia, nobody does that. In Ontario, probably 15 years ago, it was about 50-50. If it wasn't kind of a deep foundation, they would put some rebar in it to deal with the bending from soil, but they would do a masonry foundation wall. It's allowed in Part 9 of the building code. You can see that there. I'm seeing people pull away from it more and more now. Probably just because concrete trucks are easier to get wherever you want. It's more the norm. The availability of masons has fallen off, all of those things I've said. But you could still do kind of a residential foundation wall in masonry. And you see it a lot for cladding, whether you're talking about brick or masonry itself. So how do you go about picking what material you use to design your building? You can say, well, we'll ask the engineer, but often you need to have made that decision long before you come to your engineer. And even the engineer is looking at many of the same precedents you do. They might suggest an alternate or two or modifications on things, but ultimately that decision is coming from the architect, usually from some input from the owner. So obviously, precedent. If you're building a 7-story condo and you say you want to build it out of a new material, people will be like, okay, but why? Because a concrete condo is ubiquitous, and it's ubiquitous because it's the cheapest and it's the easiest and it can be built the fastest and people know exactly what to expect. But that started happening probably 6 years ago. That literally started to happen. People started saying, I don't want to build my 7-story building, my 7-story condo out of concrete. I want to build it out of CLT. I want to build it out of a mass timber material. But that wasn't the norm, and there was problems with it. People had to fight for it. So going rogue is not where you start. You have to have really good reasons. So precedent, always a good place to start. It's a precedent usually, and we're not talking about the precedents the way you talk about them, which usually means you find one unique kooky building that does all kinds of crazy cool things and pushes all kinds of boundaries. I'm talking about precedents, all the precedents for that building type, or the majority of the precedents for that building type. So you'd start there because it's the cheapest, because it's the most normal. Availability of materials. Like I said, right now people are trying to build decks in their backyard, and there are places you just literally can't get wood. So people are thinking about doing stone terraces where maybe they build up soil and put stone down instead. You know, you have to weigh in where you live and what's available. I grew up in Nova Scotia, and whenever we drive to my grandparents' place, there was this place that I always called Bricktown. It had a real name. I don't know what it was, but that town literally had a brick plant in it. And every single house in that town was built out of brick, where I was used to everything being built out of wood with vinyl siding on it. So that little town really stood out to me because they had brick down the street that they were probably given relatively cheap. They had no transportation costs. They didn't have to deal with a markup through a series of vendors. So there's real advantage to looking at that. Cost. What material is most expensive at that time? I told you about that project I did in 2007, 2008, where we designed it in steel, and steel had a blip in the market where steel went through the roof. It doubled in price for a period of 3 months, and we ended up having to redesign the building in concrete because concrete was cheaper. Just flat out, nothing else. Steel was too expensive for that brief amount of time. Fire resistance. What's the fire resistance on the building? If it needs to have a 5-hour fire resistance, there are some materials that might not lend itself well to that. Heights and spans. If you're doing, kind of your standard story-to-story height with 6-meter spans, concrete's going to be the way to go. If you're doing something with 12-meter spans, you're going to want to look at a steel building. What are the occupant loads and the self-weight of the building? So what are we putting in that building? What are we doing to it? That can have implications on what material we pick. Depth of floor sandwich. We talked about how concrete has a really shallow depth of floor and steel has a deep one locally, but steel can notch up around. So what does that mean for your building? Serviceability requirements. If you have something that needs really highly refined serviceability requirements, I think I told the story of Gold Ring, where we had an MRI on the 4th floor supporting an Olympic weightlifting floor below it, and we were actually hanging the 3rd floor. So it wasn't like the vibration had to go out and up the columns and come back to it. It was literally suspended from where the MRI was, which is highly sensitive to vibration. I'm lumping vibration and serviceability into the same kind of category here. And so we had to really look at that, and locally, under the MRI and the Olympic weightlifting unit, we did massive chunks of concrete to deal with that. And then we had to suspend those bits from our steel framework. So that can have a play in what we're building with. Dynamic loading. So this is that ability to move with our loads, which sometimes mean we can dissipate some of the energy or the amount of load our building actually sees. And this is for seismic design. I always say that engineering hasn't had that many advancements in the past 150 years, except in material science and earthquake engineering. So the way we understand the behavior of buildings due to earthquakes, the way we understand the way the soil moves due to earthquakes, and the way we understand ductility and dynamic loading due to earthquakes has a real advantage. Soil conditions. If we have really crappy soil, that might change the way you build your building. What are our drainage requirements? And like I said, rentability. If you have a big concrete column and floor space is at a premium, you might want to go with a steel one. If your and that meant your height to height or your ceiling, your floor sandwich increased, so you could go to steel, that might be okay. What if they didn't mind so much losing floor space, but they could only build to a certain height, and our floor sandwich for steel was bigger than concrete? Maybe we can fit one less story in steel. That would have a big impact on rentability if we could sell one extra floor in that same maximum height. So there's trade-offs. It's not always the same answer. And I cannot tell you what is the right element to pick. We do not know what is the right material until we look at that system and that building. Sorry, there's just all the parents who are trying to homeschool their JK and SK, their kindergarten kids. There's messages flying around almost on the daily about how we handle it and what we do. So I'm getting some flooded with questions about what we're doing here. And right now I'm just ignoring it. So I'm going to keep talking to you guys. So let's talk about the structural elements. I know that this is a dry lecture. I get it. I'm going to try to gloss over some of this, and some of them are really going to repeat for each element. So structural elements, we have floors and roofs. So those are the things that are in the flat plane parallel to the ground. That can be the floor elements, the deck elements, the beam elements, but all the things that span us to our perimeter systems or our columns. We have our columns and walls. Those are the things that go up and down that take the loads from our floors and roofs and start to transfer them down the building. We have our bracing elements. That's what stops our building from going back and forth or from rocking and tipping over. That is our lateral load resisting system. Slide 15, I'm going to add that bracing. I'm really talking about lateral load resisting system, just because I want you to start hearing that term. I really like questions about lateral load resisting systems, and I make it about as easy as I can possibly frickin' make it for you, because I need you to understand that you always need a lateral load resisting system, and we're going to talk about that. Foundations. Foundations are kind of all of that works below grade, and then cladding support and miscellaneous elements. So that's all the things that kind of supports the secondary elements that we don't think of as the structure itself, but that are supporting other elements within the building. So what are some typical floors and roof systems? Again, a lot of this is going to be repeated, but reinforced concrete slabs. So we have a big swath of concrete that's got plywood underneath that we pour concrete on, and in that concrete we've got pieces of steel at the bottom and often pieces of steel at the top. That steel is doing a couple things. It's strength for us, and it helps control where our cracks happen. Concrete always cracks. It always 100% of the time cracks, but putting reinforcing in can help control how many cracks and how much each individual crack is. Another system can be metal deck on beams and purlins or joists. So metal deck is our kind of corrugated material. It spans in one direction, and it would span to a series of beams. So if I wish I had something kind of nearby handy that I could talk about, but it's really rigid in one direction and not rigid in another. If you picked up, actually I have a piece outside, maybe I should find a picture of it and show you how it's rigid in one direction. But if you take kind of a piece of corrugated cardboard, if you bend it, if the corrugations are going this way, you can bend it easy this way, but if you turn it and bend it in the other direction, it's going to be much more stiff. And that's really what our metal deck is doing. And it spans in one direction to our beams or our joists or our purlins. We can have sheathing or decking with light gauge steel framing or wood. So that would be a thin piece of plywood that is supported by a series of small elements. 16, I'm going to add light gauge framing and wood joists. So what's the role? Why do we have a roof? I mean, obviously, I think you understand why we have a roof, but let's talk about it. Let's think about what the engineer is thinking about. So it's to support the environmental loads. So we've got snow and wind. It's got the self-weight and the roofing on it. And we might also even have people up there. We want that load to get over to the columns so that ultimately we can get that load down to the ground. We want that load to go out in reactions into the ground. It needs to support the building envelope. So that's our roofing and any insulation. It often slopes to drains. Now, there's a few ways we can do that. We can actually build it so that it slopes to a drain, or we can have our structure that we build up something else on top of it to slope to a drain. It needs to have diaphragm action. So if this is our roof, what we don't want is it to rack like this. We want it to be rigid like this. So we want it to stay as a square so that it can't skew and turn into more of a diamond shape. So that it has to have a diaphragm. It is often a diaphragm. And sometimes it might be part of our fire separation system. The floor, very similar, probably less about environmental loads and more about occupant loads. Again, we're trying to get those loads to the walls and columns. It needs to provide our wearing surface or provide our surface for our finishes for our covers, for our floor coverings. So if we have tile going on it, our structure often needs to be the thing that supports the tile. Maybe it is the exposed finished surface, and then it is the surface that feet actually touch. Again, it needs to be part of the diaphragm and is usually part of our fire separation. So what do we consider when we pick our floor and roof system? And you're going to see so much of this is the same as what we pick for our material overall. So when we're picking our system for a floor and roof, the number one thing is, what's our building material? What are we building our building out of? If that doesn't work, if the overall building material doesn't work locally in that zone, then you might go rogue. But otherwise, the number one answer, whatever the building's being built out of. After that, maybe fire resistance is important. Do we have a particular span that's longer than the others? What's the occupant load? Like I said, in that Olympic weightlifting floor, even though it was serviceability, there was also an awful lot of heavy loads coming down that we needed that. If it wasn't even about vibration, that zone right there needed to be more heavily reinforced than the rest. What's the depth of our floor sandwich? That might change something. serviceability, drainage, future flexibility. Do they think they're going to come in and put a hole in that building? And it's not at the bottom of the list for any particular reason, but it is super important that architectural considerations can be a big part of it. If your architectural considerations work with all of these things, great, problem solved. But after you've thought about all this, if you still have a problem because it doesn't match your architectural consideration, then maybe it's worth making a change. Columns and walls often can be reinforced concrete for both our walls and our columns. You can have concrete block or stone or masonry walls and or columns. Structural steel would really only be a column itself. You'd infill something else for the walls, and it wouldn't be structural for our gravity system or the thing that's putting all of our load down into the ground. A wood stud bearing wall. So what we do there is we have all kinds of little columns very close together. We might also still need more columns, but we have a lot of columns really close together, and that's kind of the principle behind our stud bearing wall. We can build that same stud bearing wall out of light gauge steel, which is the steel market's kind of competition to wood construction, where they basically make little kind of steel elements out of cold form steel that match the kind of the section properties or the size dimension, the area of our wood elements. So instead of a 2x4, there might be a channel that matches the dimensions of the 2x4, the outside dimensions. What's the role of the columns and walls? Well, they take all of that load from the floors and the roofs and transfer them down to the foundation. And 21, and sometimes they're part of the lateral load resisting system. So if we have a braced frame, when those try to get pushed over, those columns can be much more impacted than maybe other columns in the system. It also will support the cladding, which means if the wind is blowing on the cladding like this, and it's connected to a column, that column is going to have wind load on the side of it. So what's the burden on the compression element? So these are our columns and our walls. Maybe I'll just clarify that. Columns and walls, just so you know what we're talking about when we say compression element. We don't want it to squash too much. We don't want it to buckle or pop out sideways. We don't want it to deflect too much. And if there is a wind load on it, we don't want it to bend too much under the wind load. So that's the job that we need to do. We need to make sure it meets all of those criteria. So columns, this kind of lines up with the other slide that I already did. Columns are often for steel, could be steel wide flange, I shapes, hollow sections. We're going to look at all of these going forward. This is more just to start hearing the sounds. We can have crazy shapes. We could even make trusses we could even make columns that are trusses. Wood, often sawn lumber screwed together to make one bigger element. Engineered wood products, and like I said, the built up elements. Concrete, they can be plain if they're just in compression, but that is not the normal thing to do. It has no ductility. You would rarely do unreinforced concrete. Often it's got its steel in it. Masonry, same thing. So a masonry column would often still have reinforcing in it. Load-bearing walls, reinforced concrete, masonry, steels, wood stud and plywood, or steel stud. We don't do steel walls very often. That's not, and this is the norm. That's not to say we don't ever do it, but it's not the easiest, and we have to worry about buckling, and there's all kinds of reasons why it doesn't lend itself well to do a steel wall. We'll understand more about that when we start to look at actual calculations. What other systems can you have for those gravity systems? Well, you could have a combination of walls and columns. That's pretty normal and common to do. You can do a hanger. So Goldring, for example, we have Elements that are gravity elements, but they're not under compression, what we've done is hung the second and the third floor from the bottom of the fourth floor. So those vertical elements are not compression elements, they're actually tension elements. They're hangers hanging from the underside of the upper building. You can do a transfer beam. So if I have a column coming down, and it's coming down from every floor, and then at the ground floor, we want that to have no column there, we can put a transfer beam in. So we take this point load and we transfer it out to 2 new columns over here. So that is still now taking gravity loads from the rest of the building above. Ultimately, what we're trying to do is get all the load out into the ground. So perimeter walls, again, a lot of this is kind of common sense. It's more just writing it to kind of if you need to go back and have a self-check. Above grade, the perimeter walls of a building, so these are ones that might actually be an envelope attached to it as well as a structural system. We do masonry walls a lot for the exterior of buildings. Schools, you see it a lot. Concrete, precast, and wood or metal stud walls. Perimeter walls below grade tend to be a little bit different. They're almost always reinforced concrete. If you're doing a Part 9 building, you might be able to get away with plain concrete or masonry. And if you go into an old building that was built a long, long time ago, you might see a preserved wood foundation. Again, that is not the norm. And that would be one that kind of had wood slats installed where everyone is in bending, but that would not be the norm. So how do you pick your columns and walls? Again, what is the rest of the building built out of? So it's building material. What is the floor and roof system built out of? You're probably going to match that if you can. Again, the availability of materials, fire resistance, what's the height? Maybe you need to make a change because in that one spot, there's a really high zone. So that can have a play in it. Maybe that needs to be different than everything else. What's the laterally unsupported height? Meaning that there's nothing kind of bracing it on the sides. Load might make you have a specific requirement change. Rent, like we talked about, and again, dynamic loading. So these are very similar to some of the other things we've been seeing, but again, I just wanted to point them out specifically for columns and walls. So how do we go about designing it? When an engineer gets a set of drawings from an architect and we have to design the supporting system, so these are our gravity systems, what do we look at? Where do we put our columns? How do we pick where to put them? Well, first thing we do is we look and see if there's spots inside the architectural features where we can hide our elements. So if we have all kinds of weird spots around the building that we can hide a column, maybe that's the way to go. If it's available, we'll pick a regular layout. That's going to make absolutely everything else the easiest. It's going to make for the quickest construction. It's going to make for the shortest lead time. It's going to make for the cheapest cost. It's going to make for the cheapest engineering fees because it's going to standardize everything. And it might mean you can get particular products that are standardized cheaper. So a regular layout is going to be a good place to start. In fact, I'm going to change those two. I'm going to reorganize. I'm going to switch the spots on those. What's the lateral load resisting elements? So if they are part of the lateral load resisting system, we might have very specific guidelines for designing those elements. They can impact the load greatly. So if we have 2 columns with cross bases in here, they have, as this tries to rack like this, you can imagine the whole thing is trying to tilt. One side is in compression and one side is going to be in tension. So that can have an impact on how we design that element. Repetition. If we have 50 columns that are all the same, that's going to be really handy. Or if they are all pretty darn close to the same, we'll design the worst case one rather than refine it. or if the worst case one has a pretty standard column size or a thing that's relatively cheap, we'll go with that. Does it happen over multiple floors? If so, if we have one column that goes from ground to level 2 to level 3 to level 4, rather than break it up into 3 discrete elements, we might make it be one continuous element. That can change the design of it because now we've got fixity at those 2 points. So we can change the design. Some of that is feedback back and forth with the contractor or the fabricator and the engineer, because we can't anticipate where they're going to splice their columns. On a 2-story building, you can probably assume that they're all going to come the same size. What happens though if this only has 50% of the load of this? Well, maybe it's worth making the change there. But if they're all relatively similar, it's cheapest to bring one element. If you get enough of a reduction in material due to changing it from floor to floor, that's when you might think about making that splice at a floor. And again, minimizing transfers. So that's that. We've got 2 columns here, a beam here, and another column coming down in the middle. That is an expensive thing to do. So trying to eliminate that possibility. So having our columns go from the roof all the way down to the foundation in the same spot all the way around the building is going to make for the cheapest system too. So we're going to touch on lateral load resisting systems now. So you need a lateral load resisting system on every floor, in every direction of every building. I guarantee you that this question will be on the exam. It might even be question 1, and it is so important that you understand this. I will probably even tell you what the answer is. I might have the same answer every time and all of them are right. I have done this in a way where I have literally said what the answer is, and people have disagreed with me. Back when we used to do this exam as a paper copy, I said, is it A, B, C, or D? A was every floor, every direction, every building. B was A is the right answer. C was really, why are you still reading? A is the right answer. And D was, we never need one. Ha, 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 I'm joking. The answer is A. And I had a student say, none of these are right. You're wrong. We don't always need a lateral load resisting system. And they didn't choose any of the options. I was blown away. You always need a lateral load resisting system. Your building's 1 story high. You don't want it to tip over. That's because you need a lateral load resisting system. 2 stories high in both directions. You need a lateral load resisting system on both floors in each direction. You have 1 tiny little blob of a building. Doesn't matter. You need a lateral load resisting system in each direction. So every floor, every direction, every building needs a lateral load resisting system. So what's a lateral load resisting system? A lateral load resisting system is what carries our wind and earthquake loads from the floor diaphragms down to the foundation. So let's say we have wind blowing on a building like this. We have a series of floors where walls are spanning in between the floors. The wind blows on it. Half of the floor below and half of the floor above is going to span down to that floor. Now this floor wants to go that way. That floor wants to go that way. That floor wants to go that way. Each of those floors is trying not to rack and plan. That's our diaphragm. We're going to spend less time talking about that. But then that whole floor still wants to move. We need something to stop it from moving. It's funny, I taught my 4-year-old the term stability. The lateral load resisting system often keeps our building stable. He now goes around asking me, is this stable, Mummy? Is this stable? And when he falls over, he'll go like, I wasn't stable today, Mummy. So stability and lateral load resisting systems is something we understand. So keeping the building square and plan, that's the diaphragm that I was talking about. But mostly right now, I want to talk about what happens in the walls around the building. There are a few ways we can design those, or a few different things that are common to us. The burden of the lateral load resisting system, to not fail under our lateral loads. It's to prevent excessively deforming, so that's our serviceability requirements. So this is our strength requirement. This is our serviceability requirement, and it needs to not tip over or slide as well. That is our stability requirement. So the lateral load resisting system has three really important things to do. It helps keep our building strong, it helps keep our building stiff, and it really helps keep our building stable. So what are the most common types of lateral load resisting systems, or our LLRSs? Walls. If you have a wall, it is probably a lateral load resisting system. And on a lot of houses, even 20 years ago, we didn't design lateral load resisting systems on houses. Nobody did. The building code has realized how important that is, and building departments have really realized how important that is. So the materials that often have walls are concrete buildings, because our wall is also our structure. Masonry buildings, our wall is often our structure, which means it can be our lateral wall as well. And wood buildings have studs and plywood. That plywood can be our lateral load resisting system. We can have braces. Our braces can come in all sorts of forms. We can have crosses, we can have one at a diagonal that can go in tension or compression. We can have a 3-pinned arch. It seems surprising, but a pin here, 2 pins here, and a pin here is still going to be stable. The most common place you see that style of construction is hockey arenas. Those big span system buildings are big employers of the 3-pinned arch. It's probably their main way of designing buildings. And then the last one that is the hardest to do, and I'm gonna say don't do it unless you have to because it's big and expensive, and I'm gonna show you slides of what that looks like in one of our later lectures this term, but moment frames. So moment frames, we essentially usually make a box, or we make a box like this, where we connect those corners together. If you need a lot of glue building your model, you are probably designing a moment connection. Moment connections are really hard to fabricate, even in steel, which is the easiest one to fabricate. Concrete, moment connections are really easy to make. It's really hard to make them strong enough. So we inherently get a moment connection when we build with concrete. But now, once we have a moment connection, we have to make sure it's strong enough for the load it attracts. Because once it's there, it attracts load. And once it attracts load, we have to make it strong enough to resist the load. So the common lateral load resisting systems, shear walls. In fact, I'm going to add that note that when we're talking about walls, it's shear walls. Bracing, moment frames, and A-frames. So how do we pick our lateral load resisting system? Industry standards for the building type. This one is kind of interesting because it's not always the same material as the rest of the building. You can have a steel building with a concrete shear wall. If we have a steel building with a concrete core, we are probably going to use it as our lateral load resisting system. So these are the conditions where our lateral load resisting system is not always, but sometimes different than the base building. Flexibility, or the ability to change our design up. What are the applied loads? How big are the loads? If we need ductility because seismic governs, maybe we want steel just because it's the easiest to kind of detail around that. And then, what is our floor and roof system? If all of those other things are irrelevant, we'll probably go with whatever our floor and roof system is. So what are the lateral load resisting systems for common building types? For wood frame construction, we're going to have a perimeter plywood wall with wood studs. Hotels and condos, probably if they're made out of concrete, they're going to be a concrete shear wall. Even if they were made out of steel, the core or the stairwell is probably made out of concrete, and we'd still use that as our lateral load resisting system. Schools, load-bearing masonry shear walls. Commercial buildings, concrete shear walls, even tilt-up walls. So tilt-up walls are interesting. It's rarely done here in Ontario, but in Nova Scotia when I left, it was probably the most common for commercial buildings, where they build the slab on the ground and they leave it outdoors. It's built there on the ground. And then they put a bond break down and they cast the wall laying down on the ground, and then they tip it up into place. So a lot of wood construction is done that way. What's really nice is you can get a really beautiful finish on it. Industrial buildings and warehouses, remember, those are predominantly built out of steel, so they often have steel braced frames. A high-rise office building, well, if it's got concrete walls, it's going to use shear walls. If it is steel or concrete and it's got a concrete core, it's going to be a concrete core or shear walls or a tube. Sometimes if it's tall enough, we'll use the whole tube and not just the separate walls. If it is a steel building, we might have a core, but that might not be enough, and maybe we have steel bracing as well. And then arenas, moment frames, or those A-frames that I talked about are probably the most common. So what can't we do in Toronto for lateral load resisting systems? There's not much we can't do ever. I don't like to say we can't do it, anything. But seismic is one of our lateral loads, or earthquakes is one of our lateral loads that actually has some heavy kind of limitations on what we can and can't do. And it changes depending on where you are. Toronto is not a high seismic zone. What we can't do is have a weak story. So even if it's not part of our lateral load resisting system, if we have shear wall, shear wall, shear wall, shear wall, shear wall, and the ground floor we want to be completely open with just one little braced frame off to the side, even if it's strong enough, we're not allowed to do it. A floor cannot be a floor below. You can have stronger ones at the bottom than you do up above as long as they're strong enough. But the ones below, even if it's strong enough, can't have less than 10% of the floor above it. We also can't have too much torsion, or the building can't twist too much. Those are really the only limitations for seismic in Toronto and kind of southern Ontario. In high seismic zones, we can't shift the lateral load resisting system. So if this is the side of our building and we have brace frame here, brace frame here, brace frame here, and at the ground floor, we want to shift our brace frame to be over here. In Toronto, we can put a drag strut and take those loads down, transfer it across this and out of that braced frame. In high seismic zones, you're not allowed to do that. Your lateral load resisting system has to be in the same place all the way down the building. The other thing that high seismic zones do is employ something called capacity design, where we actually make sure the building isn't over-designed. We allow it to be ductile and have upper and lower bounds on the strength, because if it is over-designed, it ends up being too strong and can actually attract more seismic loads. It means it ends up being too stiff, and we don't want it to be too stiff because then it doesn't move. In Toronto, even it's quickest to design it exactly as it is, just to design it for as stiff as it needs to be strong enough. So in Toronto, that's often the cheapest thing to do. In high seismic zones, we're not allowed to do that, and the burden of the design of those systems, the engineering cost, can double or triple the engineering fees to design for capacity design. But it can often have a big implication on making the building safer and also lowering the cost of the building. So as much as the engineering fees might go up, you can see reduced cost in the overall building. So that's the end of the lecture. I'm gonna add kind of a wrap-up slide and repost this for you guys. We're just under 2 hours. I know it was dry and boring, and I apologize. Next week, there's going to be way less information, but we're gonna look at a ton of pictures. Again, just pictures from the internet of basic construction types. If you are not familiar with basic construction, that is going to be such a good lecture for you to pay attention to. People hear that it's just a bunch of pictures and often fade off and don't pay attention, but I find it's the people that already know how things go together tend to pay the most attention to that one. If you are uncertain or uncomfortable with construction methods, I recommend you take a look at those slides because I'm going to show you normal and I'm going to show you not normal. I'm going to post this video. I'm also going to go back and you might see that some of the slides have a few additions compared to what I showed you in this. It's not going to change anything for the assignment, which is already posted. But you'll probably just want to, if you've already downloaded this, go check, downloaded the lecture slides, make sure you go and download the updated one. It's just going to add a few clarity or maybe a few kind of additions of words that I thought helped crystallize the thought in the slides. So, sorry for the boring lecture. Next week, possibly even more boring. But after that, we are going to go like gangbusters. The math is going to start fast and furious, and we're really going to start digging into things. So I will see you guys next week.